in order to do multivariable calculus, one of the first things that we need to be able to do is we need to be able to define and work with objects in three-dimensional space. So in this video, we're going to introduce the three-dimensional coordinate system. It's a natural extension of the regular Cartesian plane that you've been using to graph functions and equations ever since you learned how to graph. And we're going to look at a few of its basic properties. In the case of the two-dimensional plane, you have the x and y axes, which are two lines that meet at a right angle at the origin, and every point is described as an ordered pair given their distances from those two lines. So for a three-dimensional coordinate system, we're going to want to take three lines that are all perpendicular to each other. So in order to do that, we might start with the standard plane. Right, so let's say this is our origin right here. So we want to start with the x and y axis. So I'm going to start with the x-axis, which I'll label as x. And that's going to be the positive x-axis. The negative x-axis I'm going to label as the dots. A lot of times we're not going to include the negative parts of the axes because the picture will be a little bit too complicated. The y-axis then needs to come into play, so I'll draw the y-axis over here, and the negative axis, negative y, goes over there. And so the way to visualize this right now is think of these two lines that I've drawn, the x and y axis. Think of these as lying on your desktop or your tabletop in front of you. So these two lines kind of spread out on a flat surface. To define a three-dimensional coordinate system, we want to find a third axis, which we'll call the z-axis, which is perpendicular to both of these. And so if the x and y axis are both flat, it makes sense that the z-axis should be vertical, and that would then create a right angle with both the x and y axis, which are horizontal. And so when we do this, if we think about it, we actually have two choices. If I have a vertical line through that origin that I've created, I could have the positive z-axis pointing up or the vertical z-axis pointing down. And so we're going to choose to have the vertical z-axis pointing up. And I'll explain why in a moment, or at least the convention as to why. And so, of course, that means the negative z-axis points down. Right? So this is what our standard coordinate system is going to look like in this course. We're going to have the z-axis pointing up, we're going to have the y-axis pointing to the right, and we're going to have the x-axis pointing sort of down and to the left. And, you know, in some cases we'll rearrange this, but we really want them to be organized in this way. And so once we have this system, we can plot points really easily. If I have a point, let's say 2, 3, 4, right, an ordered triple, right? Just like in the Cartesian plane, these numbers are going to tell us how to get to the point along the axes. So the first coordinate of my point is 2, so we're going to go along the positive x-axis to 2. So we're going to travel out here. And then we're going to go on the y-axis for 3. That's our y-coordinate. Right? So we're going to go 3 units in this direction. All right, so this ending point of the segment I just drew would be the point 2, 3 in our normal coordinate system. And then the third coordinate here is 4, which means we're going to go up 4 on the z-axis. So we end up at a point right around here. Right? Now, of course, this is really hard to see in 2 dimensions. You can see it almost looks like I drew that on the negative x-axis. Right? But if you have to really think about what this is doing three-dimensionally. We went 2 units along the x-axis, then 3 units along the y-axis, and then 4 units directly up. Right? And so this point is 4 units above the standard XY plane, which would be the desktop or the tabletop in front of you. Now I mentioned that there was a reason why we wanted the positive z-axis to go up from the picture that I drew previously. And the reason is something that we're going to call the right-hand rule. And the right-hand rule is illustrated in the following picture. So in this picture, we have the x, y, and z axes oriented the way that I had just drawn them. And the reason that we call this the right-hand rule is that if you take your right hand and you wrap it around the origin so that your fingers point from the positive x-axis to the positive y-axis, right, which is what's happening right here. The fingers are pointing that direction. The positive z-axis is in the direction of your thumb. Right? In this case, the thumb would be pointing upward. Right? Now, there's really no reason why this has to be the way that it is. We could certainly define a coordinate system with the left-hand rule, which would then have the thumb pointing down. However, the convention for everyone, for mathematicians, for physicists, for engineers, the convention for everyone is to use a right-handed rectangular coordinate system, which is this one here. And so everything that we do in this course will be based on the z-axis being pointed in this direction. If you ever encounter a left-hand system, which does sometimes occur, then a lot of what we're going to do just needs to be done backwards. Things become negative and things like that. But everything we're going to do relies on this right-hand rule. Right, so now that we have the x, the y, and the z-axis, and we can plot points using those three, the next step is to introduce some basic planes that will be helpful as reference planes, just like the axes will be as reference lines. And so the three basic ones that we can introduce are called the coordinate planes. Right, and there are three of these. So we have what we will often refer to as the xy plane. And this will be is expressed by the equation z equals 0. And I will draw a picture. I will have a picture of these in a moment, so just hold off on 1 second for that. But we have the xy plane, and as you can imagine, this is going to be the plane that contains the x and y axis. And so all of the points that go through that plane will have a z coordinate of 0. And so that's why this equation, z equals 0, describes that plane. We also can have the xz plane. This is the plane that goes through the x-axis and the z-axis. And this is given by the equation y equals 0. And we have the yz plane, which is the plane that goes through the y and the z-axis. And all the points on that plane will have a coordinate of x equal to 0. Right, so these three planes are the three planes that we get by picking two of the three axes and taking the unique plane that goes through those two lines. Right, and here is an image of those three planes. So the xy plane is the plane. It would be the desktop or the tabletop in front of you. That's illustrated in the green here, which is the z equals 0. The xz plane is the sort of yellow or orangish one that goes through the x and the z plane. And the yz plane represents the points through the y and the z axes, or the plane through the y and the z axes, and that's given by x equals 0. Right, and so we can, often it's hard to draw planes, so we'll oftentimes use pictures or technology to do that. But in this case, these three planes are not too difficult to visualize when you're working in three-dimensional space. Right, so one really simple example we can do just with these to make sure we understand how these planes will work. Let's say we wanted to find the distance from the point -2, 3, 4 to each of the coordinate planes. All right, so we want to find three distances. All right, so if we start with the distance to the xy plane, right, the xy plane in the picture here is the green plane. And so what I need to know here, to find the distance from the green plane, all I need to know is how far up or down along the z-axis does this point move? Or is this point located? And so the z-coordinate of this point is 4, which tells me that this point is going to lie 4 units above the xy plane, right? 4 units along the z-axis in that positive direction. And so the distance of this point from the xy plane is simply 4. Right? If we then move to the xz plane, right, the xz plane goes through the x-axis and the z-axis, so that's the yellow or the orange plane in this picture. And so the distance here is how far along the y-axis this point is located. And along the y-axis, this point is located 3 units along that axis. So the distance from the from this point to the xz plane will be 3. And the last one is the yz plane. And if you're not careful, you might make a really simple mistake here. You might say, well, the xy plane, the distance is 4, that's the z coordinate. The distance from the xz plane is 3, that's the y coordinate. So I bet the distance from the yz plane is just x, so I'm going to say -2. And fundamentally, you have the right idea, but remember that distances can't be negative. So the -2 means that this point is going to be 2 units away from the yz plane, just in the negative, along the negative x-axis. So it's going to go 2 units back away from the origin in the opposite direction that the arrow from x is pointing in the picture. And so the distance here is actually 2, not -2. So we have the coordinate axes, we now have the coordinate planes, and there are some other relatively simple regions that we can describe in three-dimensional space, and that's what we're going to look at next. So in this example, we want to describe the region given by the following sets of equations. And we want to describe them in words, to say like it's the plane that has this property, or the line with this property, or whatever it is. So what we're going to do is we're going to graph each of these, and then we're going to kind of look back and see how we can use the form of these equations to sort of generalize certain regions in 3-space. For this first region, we want to describe all the points that satisfy the equation x equal to 3. So this means that we want all points with an x coordinate of 3, and the y and z coordinates can be anything that we like. And so this should be a point that is 3 units away from the yz plane, which is the plane through the y and z axis. So any point, all the points that are 3 units away from that plane will also form a plane that's parallel to the yz plane. And this plane would go through the x-axis at the point 3. And so it should look like this. So from this picture, I know it's kind of hard to tell in 2 dimensions, but this is a plane that is parallel to the yz plane. The y-axis is green, the z-axis is blue in this picture, and so it's parallel to that plane, and it intersects the x-axis, the red axis, at the coordinate of 3. So x equals 3 describes the plane parallel to the yz plane intersecting the x-axis at 3. Similarly, if I change the 3 to any other number, it maintains the same relationship. X equals -4, for example, would consist of the plane parallel to the yz plane intersecting the x-axis at -4. If I change the x to a y or a z, it's going to be the plane that intersects the y or z axis at 3. parallel to the coordinate plane that does not contain that axis. So y equals 3 would be parallel to the xz plane, and z equals 3 would be parallel to the xy plane. The second region we wanted to describe was the region given by the equation y equal to z. So this would consist of all the points in space where the y and z coordinates are equal, so where the second and third coordinates are equal. This will, of course, contain the entire x-axis, because on the x-axis, the y and z coordinates are both 0, and so they would be equal to each other. So this set will turn out to be a plane that contains the x-axis, and that it will cut directly between the y and z axis, making a 45-degree angle with each. So it looks something like this. Right? Notice that the plane does go through the x-axis, which is the red one, and it does cut at a 45-degree angle between the y and z axis. In fact, if you would orient this, which I can't do unfortunately, but if you would orient this so that the y-axis was pointing directly to the right and the z-axis was pointing directly up, which would make the x-axis pointing right directly at you, then this plane would look like a line, and it would be the line y equals z. It would cut directly through the origin and cut up at that 45-degree angle. Right? So this y equals z will be a plane that has this property. Now we will talk more about planes later, but right now we really don't have a lot of we don't have the background to be able to describe planes in general. We can talk about planes parallel to the coordinate planes, like the x equals 3. We can talk about planes like this that cut through at nice angles, like y equals z. But generally speaking, planes are much more difficult to describe, and we'll do that in a few lessons. The next region we want to describe is the region given by x squared plus y squared equals 4. Right, now, if we were in the xy plane, if we were not working in three-dimensional space, this would be very easy to describe. X squared plus y squared equals 4 would be the circle centered at the origin of radius 4. Well, in 3 space, the only thing that is different is we now have a z-coordinate that is introduced. The z-coordinate will give us the height above the xy plane, or height above or below. Because z is not in this equation, that means z can be anything. And so what we want is we want a point that will be on this circle, x squared plus y squared equals 4 in the xy plane, or a point above or below a point on that circle. And so if you take the circle in the xy plane, you move it up and down vertically, and you look at all the points that you hit, you get a cylinder. And the cylinder should look something like this. Now, one thing that looks a little weird about this is that it looks like, for example, on the x-axis, it looks like it intersects the x-axis at around 3. That's actually just the nature of the angle that we're looking at. But this cylinder, if we were able to sketch it on the xy plane, it would intersect at 2 on each of these axes, and at -2 as well. So if we were able to look down from above, we would see that this cylinder intersects the 4 axes at these 4 particular points. So in the xy plane, this is exactly the circle, x squared plus y squared equals 4. At any other level, above or below on the z-axis, we also get a circle that looks exactly like x squared plus y squared equals 4, just lifted above or pushed below the xy axis. So x squared plus y squared equals 4 is a cylinder. The last region we want to describe is x squared plus y squared equals 4 and z equals 3. We just saw that x squared plus y squared equals 4 is a cylinder that intersects the xy axis in the circle x squared plus y squared equals 4 and has any possible z value. Well, if we introduce an additional requirement that z has to be 3, this means we want all the points on that cylinder in which the height, or the z-coordinate of the point, is exactly 3. So we need all of the points on the cylinder that are 3 units above the xy axis. And those points consist of a circle. Right, so here we see a circle that's centered at the z-axis. So it's actually the center of this circle would be the point 0, 0, 3, be 3 points above the origin. And it has a radius of 2. So if we would look straight down above, looking down the z-axis, this circle would look like it lied in the xy plane, and it would look like x squared plus y squared equals 4. Right? So the way that you can think of this circle existing is that that we take x squared plus y squared plus 4 in the xy plane, and then just shift that circle up 3 units in the z direction, and we hit this circle here. Right? Now, in these 4 pictures, in all of these, and a couple of times I've explicitly said it, it's really hard to see these without being able to move the screen around and be able to look at it from different angles. So on the course webpage, I am going to post the same GeoGebra applet that I use to graph these 4 regions. And if you want, you can open them up and you can play around with them. You can look around from different angles. You can confirm, like for example, on the previous one, that cylinder does intersect the x and y axis at plus or minus 2. You can confirm that this circle is exactly what I'm saying that it is. Unfortunately, I can't get those applets to work in the videos, so you'll have to go there separately. But I will post those so that you'll be able to play around with them as we go.